How you doing, guys? Welcome to another video. This is topic 7, equilibrium, and in this one we're looking at Le Chatelier's principle, and this is the first video of 2 about LCP. Let's go. Okay, topic 7.1, what is Le Chatelier's principle? We look at applications of the principle, we look at predicting a shift using LCP, and then we only are looking at a change in concentration in this video. The IB understandings and applications and skills focus around the concept of applying Le Chatelier's principle, so that's what we're going to focus on. Okay, Le Chatelier's principle. It's basically a general rule that helps us predict what's going to happen when an equilibrium system is exposed to a stress. And the stress could be concentration, pressure, volume, or temperature. Le Chatelier's principle says that if an external stress is applied to a system at equilibrium, the system adjusts in such a way to partially oppose the stress. And partially oppose is a very important term. When we say that the system shifts to the right, we're implying that a forward reaction will occur. So we're reading the equation, reading from left to right. So if it shifts to the right, that means it's a forward reaction. If it shifts to the left, that means it's a reverse reaction. Now we can also describe this as a net forward reaction or a net reverse reaction, and either of those terms will be fine. If we were talking about a net forward reaction in this reaction, we would be saying that N2 reacts with H2 to form NH3. And when we stress that it's a net forward reaction, we don't need the double-headed arrows anymore. We're saying it's moving in that direction. So what will happen if we increase the concentration of a reactant or product? So iron thiocyanate dissolves readily in water to give a red solution. The red colour is due to hydrated FeSCN2+, and undissociated Fe3+ is pale yellow, and SCN- is coloured. So we can monitor this by using our eyes. So what happens if we add some sodium thiocyanate, a source of SCN- ions, to the equilibrium system? Well, the stress is an increased concentration of SCN-. So what have we done? We've increased the concentration. That's the stress on the equilibrium system. Now, what's the system going to do? Well, according to Le Chatelier's principle, the system is going to try and partially oppose the increase in concentration of SCN-. How is it going to do that? Well, the only way that this equilibrium system can oppose the increased concentration of SCN- is to try and reduce the concentration of SCN-. So that means that we're going to see this reaction shift to react the SCN- with Fe3+. So we're going to have a net reverse reaction going on here. We've increased the concentration of SCN-, so the system wants to partially oppose that increase by trying to decrease it. So we're going to see the system shift from right to left. So the SCN- is going to react with the Fe3+, and we're going to form some more FeSCN2+. So we're going to get a net reverse reaction. So a net reverse reaction occurs, and whenever we say the terms a net reverse reaction, we want to write what that equation is. Now when I write this net reverse reaction, I'm going to write it from right to left. So it's going to be Fe3+ aqueous plus SCN- aqueous forms FeSCN-. What we would see here in terms of colour is by adding some SCN- in, we're going to dilute it so it's going to become lighter, but then it's going to start to get darker as FeSCN2+ is formed. But overall, it won't be as dark as it was initially because it's a partial opposition. If we're asked to draw this on a graph, a concentration versus time graph, we need to be really careful with the way we draw in our graph. So the first thing we need to do is have in all of our reactants at a certain concentration, and I've just made these concentrations up. They could be quite different, but the principle is the same. So we've got an equilibrium system with all of our reactants and products. It's at equilibrium because the concentrations are remaining steady. If we add in a stress, like an increase in SCN-, we're going to see what I call a spike. It's going to increase very quickly in concentration. Then what's going to happen, the system is going to try and shift to reduce the concentration of that SCN minus, and it's going to reduce it by a factor of x because its coefficient was 1. It doesn't go right back down to where it started because it's only a partial opposition. Now if the SCN minus starts to decrease, then Fe3 plus, because it's on the same side, it must decrease as well. It's got no choice. The FeSCN2 plus though, well, it's on the opposite side, so if the other two have gone down, then it must go up. And they've all changed by the same factor, in this case was x. Okay, so another example using that same situation. Now suppose we add some oxalic acid. Oxalic acid ionizes in water to form the oxalate ion, which strongly binds to the Fe3 plus ions. What will happen to the colour of the solution? So we need to identify the stress. So the stress in this case is addition of another chemical, but it's not in the equilibrium reaction, so we only want to focus on what's in the equilibrium reaction. So it's a decrease in concentration of Fe3 plus. Binds to basically means it's taking it away. So we've decreased the concentration of Fe3 plus. That is our stress. Le Chateliers principle states that the system will try and shift to partially oppose the stress. In this case, the system will partially oppose the decrease in Fe3 plus by shifting to increase the concentration of Fe3 plus. Now the only way that can happen is if some of the unreacted FeSCN2 plus breaks down into Fe3 plus and SCN minus. So by shifting to the right, we're going to form more of the Fe3 plus and try and partially oppose the decrease in concentration. So a net forward reaction must occur in this situation. So again, when I say a net forward reaction, I'm going to write the equation this time from left to right to show that the reaction is occurring in that way. In terms of the colour, well, we would see a kind of red-orange solution to begin with, and the Fe3 plus, the concentration decreased. So what's going to happen is the red needs to break down into something that's yellow or more colourless. So we'll probably see a lightening of the colour here. You could say that it's either going to get lighter or it's going to get less red. Either of those would be fine. We're not art students, so we're not required to go too deep into the colour. In terms of the concentration time graph, again, I've got to have my concentration of each of my reactants and products, so I'm just making those up and I'll put those in. Remember, if we see a spike or a decrease, think about what's going to happen to the curve. So for this one, we've got a decrease in the Fe3 plus concentration, so that's going to spike down. There's a large decrease. Then what happens? The system tries to shift to increase the concentration, but it doesn't go back to where it started because it's only a partial opposition. Now, SCN minus, well, that's on the same side as the Fe3 plus, so it must start to increase. It doesn't matter that these lines cross over, that's not important. The FeSCN2 plus, well, that's on the opposite side. It's what's reacting to form the Fe3 plus, so it must go down by the same factor as the other two increased. Now, if we need to talk about a catalyst in an equilibrium system, a catalyst does not alter the equilibrium constant. Remember that the Kc value is a constant, and adding something into it, it doesn't change that value. Adding a reactant or a product, it doesn't change the value either. A catalyst simply gets the equilibrium system, if it wasn't at equilibrium, to equilibrium faster. It's not a part of the overall equation, which means it's not a part of the equilibrium constant expression. Now the Kc value, it does not change, it's a constant, so the catalyst only impacts the rate at which the equilibrium will be formed. It has no impact on the actual value. If we do have a catalyst that is required for a reaction, it will affect both the rate of the forward and the reverse reaction. So a catalyst helps to reduce the activation energy of both the forward and the reverse reaction. Remember that the only thing that can change the Kc value is a change in temperature. So here we have an energy profile diagram. If we're talking about the forward reaction, we're talking about it going from reactants to products. And if we're talking about the reverse reaction, we're talking about the products turning into the reactants. Now we've got our energy profile diagram here without our catalyst, and we might be asked to draw in the activation energy for a catalyst being introduced. So if a catalyst is introduced, we're going to have a lower activation energy. So the activation energy of the forward reaction is this bit in red, and it is smaller than what it was before. What about the activation energy of the reverse reaction? Well, the reverse reaction is going from the products to the reactants. So that's this whole bit here. That would be endothermic in this particular reaction. So the activation energy of the reverse reaction is larger than the forward reaction, but it is still much smaller than it was originally. Okay, topic 7.1, some top tips. It's a partial opposition of the stress. If we're talking about it shifting to the right, we're talking about a net forward reaction, and a shift to the left is a net reverse reaction. Thanks for watching, guys. Don't forget, drop a like on the video, subscribe for more, and I'll see you next time.